Hello students, today for class 10 number system I am going to teach you second part of the number system, fundamental theorem of arithmetic. Now what is fundamental theorem of arithmetic? But before that we should know prime and composite numbers. Prime and composite numbers. Now prime numbers, a positive integer with exactly two factors. What are the two factors? 1 and itself is called a prime number. Prime numbers less than 50, I am giving you a list. Prime numbers less than 50 are 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 41, 43 and 47. Now these are prime numbers. 15 in all. You count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 13, 14 and 15. That is 23, 29, 31, 37, 41, 43 and 47. So 15 in all. 15 in all. Okay. Now 2 is the prime number because 2 is equal to 1 into 2. Exactly two factors, 1 and 2. 1 is not a prime, not a prime number. Prime number. Now 1 is not a prime number. Why? Because 1 is equal to 1 into 1. So same factors are repeated. We should have exactly two factors, 1 and itself. And these are two different numbers. But here you see that 1 is equal to 1 into 1. So exactly one factor. So 1 is not regarded as a prime number. Now composite or composite number. A positive integer having more than 2, that is 3 or more factors, is called a composite or composite number. The number 1 has only one factor, hence it is neither a prime nor a composite number. Suppose 15, you have to judge whether this is a composite or a prime number. Now 15 is equal to, we can write 1 into 3 into 5. So more than two factors. Therefore this is what? This is the composite number. Now factors. There is factors and factored tree. Factors means there is whenever we represent a number as the product of two numbers, the two numbers are called the factors of the number. Suppose 15 is equal to 3 into 5. So 3 and 5 are the factors of 15. If you are asked to find out the prime factors, then the possible product of prime numbers which gives the number is called the prime factorization of the number. Now what is the factor tree? It is a pictorial representation of factorization done using prime numbers. For example of factor tree, suppose we are to find out factors of, there is factorize 18018. Suppose we have to factorize this number using a factor tree. Using a factor tree. Factor tree. Now 18018. We can write this number as 2 into 9009. Out of these two numbers, 2 is prime. This is composite. Now this is, for this number we can again write 3 into 3003. 3 is prime. Again, for the numbers 3003, we can write 3 into 1001, where 3 is prime. Now for 1001, we can write these numbers as the product of two numbers which are called the factors of the numbers. There is 7 into 143. 7 is prime number. Then for 143, we can write 11 into 13. Now both 11 and 13 both are prime numbers, and hence what happens? Factorization ends. Now factorization ends. So for the prime factors of 18018, we can write this is equal to 2 into 3 into 3 into 7 into 11 into 13. Now how many factors it has? Even if we are taking 1, then also taking 1, 1, 2, 3, 4, 5, 6, 7. So more than 2 factors, therefore it is a composite number. Okay, now let us come to the discussion. Fundamental theorem of arithmetic. Now what is fundamental theorem of arithmetic? You see, whenever 18018 is a composite number, how many times or using different methods, if you are finding the prime factors of this number, the same number 1, 2, 3, 3, 7, 11 and 13 will come. What will be the difference? The difference will be in the order of occurrence of the factors. Somebody may write 1 into 3 into 2 into 3 into 7 into 13 into 11. So like this, the order of occurrence of the numbers can differ. But the prime factorization is unique. You always will get the same factors. So for the definition of prime factorization, fundamental theorem of arithmetic, we can say every composite number can be expressed, means factorized, as a product of primes and this factorization is unique apart from the order in which the prime factors occur. So this is called fundamental theorem of arithmetic. Now, application of fundamental theorem of arithmetic. We can find HCF, we can find LCM, we can check whether a number can end with the digit 0 or not if it consists of course, index power and so on. For example, suppose you are asked, check if for any natural number n, 6 to the power n will end in the digit 0. Now, how to solve this one? Solution. Solution. Let x is equal to 6 to the power n, that is equal to 2 into 3 whole to the power n, that is equal to 2 to the power n into 3 to the power n. Now what we observe? We observe that the prime factorization of 6 to the power n, n belongs to natural number, has the factor 2 but does not have the factor 5. What do you know? If the number ends in the digit 0, it is divisible by 10. Now 10 has factors 2 and 5. So if the number is divisible by 10, it must consist at least one pair of 2 and 5 as its prime factors. But in case of this number, for the prime factorization of 6 to the power n, we observe that it has the factor 2 but does not have the factor 5. Hence, it will not end in the digit 0 for any natural number n. Okay? Hence, it will not end in the digit 0 for any natural number n. Now suppose we have to verify another question. Is 7 into 11 into 13 plus 13 a composite number? A composite number. Why? Now, set solution, how to solve these questions are very common in the board exam. Okay, of course this is for class 10, the continuation of this one you know. Now let for the solution x is equal to 7 into 11 into 13 plus 13. That is, we can take 13 common. 13 is present in both terms. So 7 into 11 plus 1. that is 13 into 77 plus 1, 78. That is equal to 1 into 13 into 78. Clearly, x has factors 1, 13 and 78. As x has more than 2 factors, it is a composite number. Now to find the HCF, another application to find HCF and LCM by prime factorization method. Suppose you were given a question, find HCF and LCM of 336 and 54 by applying prime factorization method. Okay. Now what to do? Of course, you need to find out the prime factors of 3, 36 and 54 separately. So let us do that. 336 and it is 54. So 336, first let us divide this one by prime factor 2. We will get 168. Again let us divide by 2, we will get 84. Again let us divide by 2, we will get 42. Again let us divide by 2, we will get 21. Of course, now we will divide this by 3, we will get 7. Now 7 is divisible by 7 and 1. Now for 54, let us divide this number by 2 first, 27. Now by 3, 9. Now by 3, 3. Now by 3, 1. Therefore, 336 is equal to 2 to the power 4 into 3 to the power 1 into 7 to the power 1. And 54 is equal to 2 to the power 1 into 3 to the power 3. Okay, now HCF. When we are finding the HCF, we will take the numbers having the least power. Here the factors 2 has power 4, here 2 has power 1, so least power 2 to the power 1. 3 to the power 1, 3 to the power 3. So 3 to the power 1. Since 7 is not present here, we can write 7 to the power 0. It means it is 1. So 3 to just 6 is the HCF. So HCF will be 6. And LCM. For LCM, remember, you need to take the highest power of the factors. 2 to the power 1, 2 to the power 4. If we compare highest power 2 to the power 4. So 2 to the power 4 into 3 to the power 1, 3 to the power 3. So 3 to the power 3. Into 7 to the power 1, 7 to the power 0 means no 7. So highest is 7 to the power 1. So if we multiply, we will get 3024. Therefore HCF is 6 and LCM is 3024. Now let us mention one thing here. What is the relation between HCF, LCM and product of the two numbers? We all know. I think you also know. HCF into LCM is equal to product of two numbers. Therefore HCF is equal to product of two numbers by LCM if LCM is given, and LCM is equal to product of two numbers by HCF. Now remember one thing, this relation exists only for two numbers. We have written two numbers. If there are three numbers, you cannot write HCF into LCM is equal to product of three numbers. You cannot write. This is true for two numbers only. Okay? So students, you follow the video very carefully, very attentively. If you have any query, you are always free to ask. Okay? So up to this for today.